Right. Thank you everybody for coming, and thank you everybody for listening on our YouTube channel. Today, we have the great pleasure of having two speakers, Ziggy Pleunis currently at the University of Toronto at the Dunlap Institute. He did his PhD at McGill University. We're also going to have another talk, or another piece of this talk, given by Chia, who is currently at McGill University and did his master's at the University of Manchester. And today they're going to talk to us about the CHIME FRB experiment. And if I'm not mistaken, I just saw a couple minutes ago on Instagram that the CHIME FRB collaboration has won the Berkeley Award from the American Astronomical Society. So congrats you guys for that good news. I hope you saw it before I did. With that, I'm going to stop talking and leave it over to you.
Thanks, Carter, for the introduction. Yeah, so I'll talk about the CHIME FRB experiment, and then Chia is going to talk about CHIME Pulsar experiment, which is running on the same telescope. And there's also another experiment, a cosmology experiment, and also a slow pulsar search running all in parallel on the same telescope. So I'll focus on CHIME FRB. Here's the telescope already in the background. I'll go into a little bit more detail later. Giving the presentation on behalf of the whole CHIME FRB collaboration. And as Carter just pointed out, indeed, today it was announced that the CHIME FRB team will be awarded the 2022 Berkeley Prize by the AAS. And if you haven't heard of this prize, it's for innovative research in astronomy. And in the past, it has been awarded, amongst others, to the Einstein Horizon Telescope and LIGO teams. So to talk about CHIME, FRB, and fast radio bursts, first have to briefly introduce pulsars. So if you haven't heard of these, they're rotating neutron stars. They were first discovered in 1967. And we detect them by their radio emission. And here's an animation of the star. And so there's emission. As the star rotates, see a pulse of emission every rotation. And so it's like a cosmic lighthouse. And how we observe this on the sky is by this pulsed emission in the time series. And so they form an important backstory for fast radio bursts, because a lot of the phenomenology is different. It's the same, not different. So an important aspect of these radio observations of pulsars is that they're dispersed by the interstellar and intergalactic medium. So it's an impulse of radio waves. And as it travels through the interstellar medium, it encounters other free electrons. And that causes this dispersive time delay that just from physics we know is proportional to 1 over the frequency squared and to the integrated column density of free electrons that it encounters. So it tells us something about the distance traveled. And here in the top left, you can see this illustrated. So this would be for a pulsar. And in a dynamic spectrum, you have frequency over time, or frequency over spin phase in this case. And you see this dispersive sweep with the 1 over frequency squared dependence. And so we have to correct for the sweep when we observe something. As you see here on the second figure, this delay has been removed. And then if you integrate the signal, you actually see this peak, this pulse. And so for pulsars, we can measure this delay, and we quantify it by something we call the dispersion measure, the DM. And so this is an important quantity, and we get it from the radio signal. And so the Earth is sitting in the Milky Way, as I tried to illustrate here on the right. And so if we observe multiple pulsars around us, we measure this quantity DM in all of the different directions. And this then tells us something about the free electron distribution in the Milky Way. And so if we do this for enough pulsars, and we know more than 1,000, we can actually make models of the free electron distribution. So this is a model here from a top view of the Milky Way, where the color is the overdensity in electrons. And so you see there's more electrons in the spiral arms, as you might expect. And so this tells us something about, in any given direction, if we observe, what's the expected dispersion measure a radio pulse should have, given its distance. And so people were observing pulsars, and then someone had the idea to look for pulsars at larger distances, so with larger dispersion measures having encountered more free electrons. And that's how fast radio bursts were discovered. And so these were first discovered only in 2007, so not too long ago. They have a similar characteristic dynamic spectrum. So again, frequency over time, you see this dispersive delay with the same dependency. The duration of the pulses is about 1 millisecond. although we are now discovering a wide variety of durations. But if you do the accounting for the time delay that we observe, only a fraction of this can be attributed to the Milky Way, because what we know for pulsars in that direction. And then the rest of the delay has to come from the Milky Way halo, the intergalactic medium, and the host galaxy. So already when the first fast radio burst was discovered, it was clear from the radio signal alone that likely these are extragalactic. And now we actually know that fast radio bursts are definitely extragalactic, because a handful of them, we've been able to localize them to a host galaxy and have been able to obtain a redshift for the host galaxy. So extragalactic radio sources means they come from far, but we can still observe them. So it means they must be very energetic. They have brightness temperatures of about 10 to the 36 Kelvin, which means that the emission must be coherent. And from our observations, we can measure that there must be about 1,000 on the sky every day that we could detect with modern day telescopes. Some interesting features are that some fast radio bursts repeat, while others apparently do not. And so apparently do not, I mean, we've observed or followed up some fast radio bursts for 100 hours or more and have not been able to detect any repeat bursts. And then some others, we do see them more often. And also we have been seeing that some fast radio bursts that they repeat periodically. And I'll come back to that later, because it's actually something that CHIME FRB discovered. So that's my introduction to fast radio bursts. They are a mystery, but they're also an opportunity. And that's because of the propagation effects that I already mentioned. And so the FRB is extragalactic. So it is born or produced in some FRB engine, travels to its host galaxy, through the halo around that host galaxy, through the intercluster medium. It might encounter some circumgalactic media of intervening galaxies, and it will travel to the intergalactic medium and finally through the Milky Way. So you get an imprint of the interactions with the electrons in all of those media into this observable called the DM, or in the time delay. And so if we measure the time delays for a lot of fast radio bursts, we can learn something about all of these media. And so it's not only the time delay that's imprinted on the fast radio burst, it's also scattering from inhomogeneities in these media, and also scintillation, Faraday rotation, which is if any of these media would be magnetic. And potentially we could also measure things like plasma and gravitational lensing. So fast radio bursts are this really unique probe or backlight to the universe, from which we can learn a lot about otherwise invisible structure. So that's just the introduction to why FRBs are interesting and why we'd like to observe them. And so where CHIME comes in is that around this time, FRBs were detected, and a group of cosmologists in Canada was building CHIME to measure the expansion history of the universe at a specific redshift range. And they were building it in at the Dominion Radio Astrophysical Observatory, and that's near Penticton in BC. It's in this natural valley, which is great for a radio observatory because the hills, they shield you from microwaves and Wi-Fi. And so you see there's multiple other telescopes already at the site. And so from a side view, here's CHIME, made up of these 4 cylinders. There's the synthesis telescope, which is an interferometer you see in the background. There's a 26-meter single dish telescope. Here in the front, you see all these poles. That's an old decommissioned 22 megahertz telescope. That's about the lowest frequencies you could observe from Earth. And here's the pathfinder to CHIME. So it's to test out some of the technologies for CHIME before CHIME was built. And so zooming in on CHIME in a different season, this is 1 cylinder. And so the reason CHIME is great for searching fast radio bursts, there's 1,000 of them on the sky every day to be observed. So you need a large field of view to have the highest chance of catching a lot of them. And that's something that CHIME has. So there's no moving parts in the telescope. It basically sees the whole sky from horizon to horizon in the north-south direction, but it focuses light in the east-west direction. So that's the cylindrical design. So the light is focused on this focal line over here at each of the 4 cylinders. And these focal lines are populated by 256 dual polarization antennas. And so that makes CHIME an interferometer. And because you have the different antennas, it's an interferometer. You can effectively repoint the telescope towards different positions within the primary field of view of the telescope. So it is sensitive, has a large field of view, and it can also apply its sensitivity to all of these different pointings. And so I mentioned the cosmology experiment is looking after the specific redshift range for the spin flip of neutral hydrogen. And so this corresponds to the frequency range of CHIME, which is 400 to 800 megahertz. Yeah, so that's introduction to CHIME. So what CHIME FRB is doing, it's taking this data stream from the telescope. It has the large field of view, and the telescope is just sitting here, no moving parts. And as the sky drifts overhead, or as the Earth rotates, depending on your field of view, point of view, what we do is we have this primary field of view of about 100 degrees by 1 or 2 degrees, and the form beams or pixels in this primary field of view. So we end up with these 1024 digital beams, and they have roughly the same sensitivity. It's better towards zenith than away from zenith. But CHIME has roughly the same sensitivity as the Green Bank telescope in West Virginia, which I put a photo of up here. And so what CHIME FRB is essentially doing is the same survey that the GBT could be doing, but then with 1024 beams in parallel. And so CHIME is doing this, it's observing 24/7 and year round. So that's a very large survey speed that we can obtain that way. And so the challenge is the data rate that we see. So CHIME FRB observes, as I said, the 1024 beams. I just put 8 here for illustration. Each beam has 16,000 frequency channels over this 400 megahertz bandwidth. We use a time resolution of about a millisecond. And so if you do that calculation in your head, you end up with 142 gigabits per second of data. And so in all of the data, we have to, the challenge is to see, is there a fast radio burst or is there no fast radio burst in this particular beam? And because it's just infeasible to store all of this data to disk, we have to decide in real time, do we save the data this 1 second around the fast radio burst, or do we just toss it out? And so that's the algorithmic challenge that we have to solve. And we're not only discovering fast radio bursts, but also new galactic pulsars. And I think Chia will tell more about this. So this is the most recent photo of the CHIME FRB team that I know of, which is from a face-to-face meeting from before the pandemic, when we all came together at McGill. It's a great team, and I've been really enjoying being a part of it. And one of the great things I think about it is that there's many of the projects, hardware, software, and science projects that have been led by junior scientists, so both by grad students and by postdocs on the team. And yeah, what I'd like to talk about next is some of the research highlights that came out of CHIME FRB in recent years. So first of all, it was new when we first detected fast radio bursts, when we turned on the telescope in 2018, that we saw FRB emission down to 400 megahertz. So it was a bit of a gamble to build CHIME in this frequency range and use it to search for fast radio bursts, because until we turned on the telescope, no one had seen fast radio bursts below 800 megahertz or so. So that was the first hint of what we were starting to do was worth it. So this was in the first few weeks of observations. We saw these 13 fast radio bursts here and everywhere else in the talk. All of the dispersive delay is removed from the signal. So this landed us on the cover of Nature, which is really cool. It's a nice photo as well. And another early success of CHIME was by finding a lot of fast repeating sources of fast radio bursts. Here's just a histogram of the repeater source discoveries. It's already a bit out of date, but I didn't have time to update it. But the total count of repeating sources is about 24. And so Arecibo found the first one and has only found that one source. And you see CHIME FRB then found the majority of repeating sources. And the reason it works really well with CHIME, there's no moving parts, sky drifts overhead every day. So we see the same sky positions every day. So if something repeats, we observe it again the next day. And so that's a good strategy, it turns out, for detecting repeating sources. That begs the question, are these repeating sources? We have only, as I say, 24 versus all of the other FRBs that don't repeat. Is that a separate population? That's something we'll have to figure out. And it also allows for an opportunity, because when you know what sky position you can look at to expect repeat bursts, that enables a lot of multi-wavelength follow-up. And you can study some individual sources in detail. And some particularly interesting repeating sources of fast fader bursts that we've been finding is, these are illustrations belonging to 3 different sources. So first, on the top left, we found this one fast fader burst towards M81, known spiral galaxy in the local universe. And this has then been followed up by other teams. And it turns out that this fast fader burst is coming from a globular cluster, which is very surprising. Because globular clusters are old, and something like a fast fader burst was thought to be coming from more of a young population of stars. On the top right, it's another fast fader burst that's very likely coming from this galaxy here, indicated by number 4, which is an NGC galaxy. I forget the number, but the exciting thing here too is it's a very nearby fast fader burst. So nearby is interesting because then you could do multi-wavelength follow-up and you have less extinction. So it's more likely that you could detect some X-rays or gamma rays from the source. And then finally, there's this other repeating source here at the bottom. And what's exciting about this one, it was only detected in November 2021, even though we had been observing the same sky position for years every day. So you see here, the plot is showing our exposure. It's about 4 minutes per day over time. So you see, we observe it, no burst. And then only here in November, we start seeing bursts with the gray, indicated by the gray vertical lines. So this suddenly turns on. And we announced this to our community of fast fader burst aficionados, and they started following it up. And so we've learned a lot about fast fader bursts by just this one source. And it's very exciting. I mentioned in passing that some fast fader bursts that repeat periodically. And we first noticed this in this one repeating source. On the top left is this figure. And there's a lot going on in the figure. But important to look at is these red triangles are detections of bursts from the source. And what we figured out is it turns out they only land in these gray bands, which are 4 days in every 16-day cycle. And so we could prove that this was actually significant. And so this is a source that just repeats, is just active once every 16 days for about 4 days. And when we followed up the source with other telescopes, we actually found that if you look at the burst arrival times, here is a function of frequency and the activity phase. So activity phase would be here the 16 days. At higher frequencies with CHIME FRB, we detect all of the bursts here in this 4-day window. But if you go towards lower frequencies with the GMRT telescope in India or with the LOFAR telescope in the Netherlands, those bursts preferentially arrive later in the window. So there's some frequency dependence going on that tells us something about the origin of this emission. And so a periodicity like this could be coming from some sort of binary orbit where maybe a neutron star would be traveling around the companion star, and you could only see the fast fader burst when it's preferentially orientated towards you. Or people have suggested it might be coming from the precession of some neutron star that produces the fast fader burst, and it processes in and outside of your line of sight. And I just put here some references for other clues as to what this source might be from follow-up observations. And so this is another exciting discovery that CHIME FRB made, and it's cited actually in part as the reason for why the prize will be that I mentioned will be awarded to the team, is that in 2020 we saw this super bright burst from a galactic magnetar, and you see the burst here on the top left. So you see it has 2 components, 1 and 2. We detected this with CHIME. And the source was actually so bright, or the burst was so bright, that we were also able to detect the same burst with this 10-meter dish that we used in the Algonquin Park in Ontario to observe sources with. And so 10 meters is big, but not that big for radio telescopes. But it could still observe this fast radio burst. And the same burst, or actually just the second component here, was also detected by this STARE-2 telescope in California that was purposely built to detect only those brightest galactic sources like this one. And this is the grad student Chris Borchinek at Caltech who worked on this. And this is a very exciting discovery because it's provides a bridge between galactic sources and those extragalactic fast radio bursts. And it had been proposed already in the past that fast radio bursts could be produced by magnetars. But people were always asking, if that's possible, then why do we never see FRB-like bursts from a galactic source? And this was exactly that missing link. And you can see this a little bit more clearly in this diagram where you look at the observed fluence of different sources versus their distance. So nearby in the galaxy, we have pulsars, rotating radio transients, and they have a typical fluence, and then fluence and distance, you can translate it into energy. So the diagonal lines here are different energies. And so this is where the fast radio bursts live. And then this is this magnetar burst. So the magnetar is called SDR 1935 plus 2154. And so you see that this magnetar burst that we detected has similar energy to the lowest energy fast radio burst. So that provides the link. It's very likely that at least some fast radio bursts could be produced by magnetars. But as you can also see, there's still a few orders of magnitude higher energy fast radio bursts. So it's not sure if all of them could be produced by magnetars. So just another sort of periodicity that we've discovered recently. So this is not the type of periodicity that I talked before, where it's the activity is periodic. But here we found these 3 fast radio bursts, 1, 2, and 3, where if you look at the time series of these pulses, there's multiple pulses and there seem to be a periodicity, or the gaps between the peaks seem to be the same, just by eye when you look at these. And it turns out that it's only significant for this burst on the left, but we also published the other 2 bursts. And here on the left, what we see is a periodic separation of about 220 milliseconds in this 3-second long burst. And for the others, it's more like a few millisecond separation, but the significance is lesser. And so this also tells us something about what might be the origin of the fast radio burst. And it's exciting, especially because these 3 fast radio bursts in all of our sources are the only ones that show this. So maybe it's some sort of special class of fast radio bursts that we detected. And so for the last bit of my talk, I just wanted to focus on the most recent group of publications from CHIME FRB, which is our first catalog. And so fast radio bursts were first discovered in 2007, up until 2016 when we started construction and development of the CHIME FRB experiment. This was what the fast radio burst sky looked like. So declination versus right ascension. All of the markers here are detections of fast radio bursts. And you see there were about 5 telescopes detecting fast radio bursts at the time, but we only see a handful of sources. And then the first CHIME FRB catalog looks like this. So this is from observations with CHIME FRB, just from July 2018 to July 2019. Again, declination versus right ascension. And all the blue circles here are FRBs that we detected that never repeated. And then the orange triangles, there are sources that did repeat. And so you see, we really quadrupled the number of fast radio bursts, and all with 1 telescope. So this has a lot of advantages, because if you have 1 telescope, you can do better population studies, because the selection function for detecting all of these bursts was the same. So from the sample, you can look at, for example, the luminosity function of fast radio bursts. So this would be the number of bursts you detect above some brightness, or above some luminosity. And so what we detect is, you see here, this alpha function is this power law parameterization of the luminosity function, and turns out it is minus 1.4, which is consistent within errors to what you expect for a Euclidean universe. And so this tells you something about the source population of fast failure bursts. You can learn things about, do they follow star formation history in the universe, or something else. And then we can also measure a rate. It's in the same diagram here on the vertical axis. So the rate turns out to be, in our frequency band, about 820 fast failure bursts per sky per day above this Pleunis threshold. And there's some other caveats that I don't have time to go into right now. But these are some things you can measure really well with this large population. And so you can also do other population studies. So we can look at all of the fast failure bursts here. I'm showing you 60, where the 30 on the left don't repeat, and the 30 on the right, they do repeat. So there's this whole zoo of structures you can see in their dynamic spectra. Some of them span the whole observing band, and some of them, they span only a fraction of it. And so here are 4 examples of studies we did based on this first catalog, and all of these studies have been led by grad students on the team. So one thing you can do is correlate the positions of fast failure bursts with those from galaxies. We do find a statistically significant correlation with the WISE and I think also the BOSS galaxy catalogs. We looked at the rate of FRBs and how it changes with galactic latitude. So it turns out there's no change. So it means we detect as many fast failure bursts looking through the plane as away from the galactic plane. It tells you also something about the propagation effects in the Milky Way. One student led a project of forward modeling scattering properties that we observe for fast failure bursts. And so this tells you something about the preference for fast failure bursts to live in specific environments. So for example, if they are preferentially living in supernova remnants or without having a lot of dense material around the source of the fast failure burst. And then finally, we also found this dichotomy between repeater bursts and one-off events, where the repeater bursts on average have narrower bandwidth, so they occupy less of the frequency range, and also they have longer duration. So this might also tell us something about these different populations of fast failure bursts. And so that's all a lot of information. I'm just trying to give a glimpse of all of the things we can do and have been doing with CHIME FRB. And along with the first catalog, we've released this CHIME FRB VO event service. It's now live. So VO events is a framework for publishing transient events that had been used by the GRB community before. You can go to this website if you want to get a note every time that we detect a fast failure burst. So you can get an email, or you can hook it up with a computer and do automatic follow-up. And we also publicly released all the data from the first catalog. You can go to the site, and we worked with the CanFAR team. It's a Canadian infrastructure for I don't know what abbreviation stands for at the top of my head, but they host our data, and you can go download it and play with it. And so that's just an overview of what CHIME FRB has been doing in the last few years. Just 2 slides for future work we're planning and working on right now. One is building CHIME outriggers. So I hope I convinced you that the strength of CHIME FRB was to detect a lot of fast failure bursts. One of the weaknesses of CHIME FRB is it's not very good, or it was not very good at pinpointing them on the sky. So the angular resolution was only at best a few arc minutes. And so we're solving this by building mini versions of CHIME, one in BC near Allenby, one in West Virginia near the Green Bank Observatory, and one in California. And so using these 3 outrigger stations, when we detect a fast failure burst at all of the stations, we can triangulate the position, and then we can pinpoint the FRBs to sub-arc second precision, which means that we not only can tell it's coming from this host galaxy, but also it's coming from here within the host galaxy. And so it would tell you if it comes from closer to star formation or on the outskirts of the host galaxy. And it also enables the redshift determination for these FRBs. And then with that, we can do a cosmology with fast failure bursts. And so just to show that this is really work in progress, this is the current state. of the first outrigger station. The metal structure is there. Near Green Bank, we have the foundations in the ground, and in California, we're a little bit behind. But this is, we're hoping to get first light, at least at the first outrigger station near the end of this year. And so this is something to look forward to. And then just one slide also to mention another project that's running on the same telescope and it's being in development, which is the CHIME slow pulsar search. So there's a lot of pulsars in the galaxy, and there's also a lot of undetected pulsars in the galaxy, especially the slow rotators. So if the rotation period is a second or longer, it's harder to find them. With most searching techniques. So the solution here is to use data from CHIME FRB, combine that data over multiple days, you stack it coherently, and then we search for pulsars in Fourier space. So this means the pulsar will transit through our beam every day for a few minutes, up to 10 minutes. But if we build up this data set over multiple days, we eventually have hours of exposure on each sky position, and then we can find all of those pulsars. So you search the pulsars in Fourier space because it's a periodic signal. You find candidates using machine learning, and then you have this catalog of all your new and known pulsars. And so this will really revolutionize searching for the specific slow pulsar subclass of pulsars. And it will search the whole northern sky for pulsars all day, every day. And then hopefully we'll find all of the dimmest and most erratic ones that can tell us then something about star formation and evolution. And so finally, I just want to mention some ways to get involved if you think this is all very exciting. So one way would be to apply for a summer student project or grad school and work with one of the members of the CHIME FRB collaboration at these institutions. As I mentioned, you could use results from our public data releases to do your own science with our data. You can subscribe to receive our VO events and plan a campaign for triggered follow-up of fast radio bursts. We're happy to collaborate with you on any follow-up project where you need any information that's not already publicly available. If you or someone you know likes to become a citizen scientist and help our search for fast radio bursts, you can go to this website and help us classify fast radio bursts. And just want to mention, we're all happy to chat, so you can send me an email or find any of the team members and express your interest, and we can talk about how you can help out.
All right, Ziggy, thank you very much for that. That was excellent. And thank you very much for the ways to get involved slide. That's much appreciated. So I suggest we hold off on questions until after the second presentation, and then we can do all the questions together. Does that work for everybody? Okay, then with that, Chairman, if you'd like to go ahead and share your screen.
Sure.
The floor is all yours.
Try 5 slides.
It's looking good. It's not in full screen, but
Yeah, neat. Okay, let me check if this works. You guys see the slides? Fine.
there we go. It's perfect. Yep. Thank you.
Okay, so hi, I'm Chia. I'm a postdoc at McGill University, and I'm here to talk about how we use the CHIME telescope to study pulsars in general. So Ziggy has talked a little bit about what pulsars are, and I'm just gonna quickly basically review about what pulsars are. So they were like very rapidly rotating and highly magnetized neutron stars that are formed from supernova explosions. Usually the progenitor stars are of like between 8 to 25 solar masses. And the radio emission comes out from the magnetic poles, and Ziggy kind of showed like how you could see them as pulses as they rotate, as they rotate, and the signals cut across the line of sight of us. And one very important thing about pulsars themselves are like they are very stable. They are very stable rotators, as in you could measure the pulse, when a pulse arrives towards us very accurately depending on how bright they are. And the brightest pulsar, you can measure it down to like a fraction of the % of the spin period of the pulsar. So what we usually try to understand about pulsars is to by measure their spin period and also the spin period derivative, which is how much does the spin period, the rotation of the pulsars change over time. So they are like very stable rotators, so the change is actually very small. But but still we could measure them very well. And so far we have known about 3,000 pulsars in our galaxy, where we usually classify them as two main types of pulsars. One is what we call normal pulsars, or in other words, slow pulsars, where the spin period is thought to be about 100 milliseconds to up to like 20s and few tenths of seconds. And these are actually what we call the younger pulsars, where the age are expected to be like below like 10 mega years, so 10 million years old. And then they had much higher magnetic field of between 10 to the 10 to 10 to the 13 Gauss. And a subclass and a second class of pulsars are known as the millisecond pulsars, which in their name suggests that they have much faster spin period compared to the normal pulsars. And they are actually an older population with a much lower magnetic field strength of between 10 to the power 8 to 10 to the power 9 Gauss. And their very fast spin periods are actually due to accretion by a binary companion of the pulsar, where you spun up the pulsar from like few tens of from a period of seconds to like periods of down to like a few milliseconds. So why do we want to study pulsars? There's a lot of reasons why we want to do them. The first of all is, as Ziggy alluded a bit, is that we want to understand the pulsar population, which gives us insight to the star formation history of our galaxy. And a second thing that we could use pulsars to do is to do general relativity tests. So some of the pulsars, they were like they have a binary companion with degenerate stars, and from that, how the pulse arrival time affect by the orbit of the by their orbital motion with their binary companion could be used to model can be used to model the Keplerian orbit between the two sorts, between the pulsar and its companion, and as well as any post-Keplerian properties that are predicted by general relativity. So in that way, we could use that to test for general relativity. And we can also use pulsars as probes to study interstellar medium, as Ziggy mentioned about dispersion measure by looking at the dispersion measures of the pulsars to try to model the galactic electron densities. And another thing that we could measure is the rotation, is the galactic line of sight rotation measure, Faraday rotation measures, which is also which can be measured by through pulsars. And another thing that we use pulsars to do is to try to use them as probes to detect gravitational waves. So what we do is that we try to measure the arrival times of a number of millisecond pulsars, which are the most stable rotators known in the universe. And by measuring the correlation within the change of arrival time of the sets of pulsars that we are looking at, we might be able to see like gravitational waves that passes through Earth and causes space-time variation. And all of these work can be done with CHIME. So a brief introduction to the CHIME pulsar system is that we have a 10-node system that uses GPUs to process observation in real time. So this effectively gave us 10 telescopes to track 10 different positions on the sky at one time, which is much more than any other observatory could do. And another thing is that we operate simultaneously with other backends. So what other CHIME experiments are doing doesn't affect, doesn't take away time from the CHIME Pulsar operations. So with that said, we are able to collect roughly about 400 gigabytes of data every day. And since operation began in July 2018, we have collected close to 500 terabytes of data. So there's a lot of data to go through from our side. So while we have 10 telescopes to use for observations, the fact that the CHIME is a transit telescope kind of limits in how we could schedule our observations towards different pulsars, as like each source are usually limited to like a transit time of about 50 minutes. And the other problem is that the pulsars are not uniformly distributed throughout our galaxy. So most of the known pulsars are located in the galactic plane, close to the galactic center. So from our point of view, it means that most of the known pulsars are located, like more than half of the known pulsars in the CHIME field of view are located within a 2-hour right ascension range of between 18 to array of 18 to 20. So we had to figure out a way to like basically manage the scheduling so that we could observe as much pulsar as possible with the appropriate like cadence that we wanted to for each source. So to solve that, we had to we built a priority-based probabilistic scheduling system to try to resolve any conflicts between different sources that between like a number of sources that transits the telescope at the same time. So we had set aside a set of high priority sources to be observed every day as long as the telescope is operating. And for the other sources, we had a decaying priority value based on relative scientific importance and the observation history of the pulsar to determine how likely a source is going to be observed during its next transit. So with this system setup, we are able to observe between 400 to 500 sources every day, where we are able to cover 75% of about 12,000 sources that are currently in our schedule within 2 weeks. And we are able to cover almost all the pulsars that are within our field of view within a 2-month period. So next, I'll talk about all the science we had done so far, all the science that we are able to do with the CHIME Pulsar system. So one of the main science project that's ongoing with CHIME Pulsar is the Pulsar Timing Array experiment, which is the experiment that uses an ensemble of millisecond pulsars to try to detect gravitational wave. So we are part of the North American Nanohertz Observatory to detect gravitational waves, which is a collaboration throughout North America to work on pulsar timing array experiment. So within nanograph, we regularly observe 45 millisecond pulsars, and we are combining the data that we have collected with CHIME with those that have been collected with the Green Bank telescope and Arecibo telescope over the past, I think, 15 years by now. And considering that the Arecibo telescope has collapsed and being decommissioned since December of 2020, that now the data that we are collecting from with CHIME is more important than ever for the nanograph experiment to continue, while we are looking into they are looking into new telescope that could take up some of the work that's done by the Arecibo telescope. So some of the contribution to nanographs from CHIME Pulsar side is that our near daily cadence in terms of observing nanograph source allows us to basically reduce the RMS noise of the arrival time of the pulsars observed over a relatively shorter timescale compared to data collected with the Green Bank telescope and Arecibo, which they usually does it on like a weekly basis instead of daily that we could. So as I've shown here, that we could get the same RMS over like 1/3 of the time due to our high cadence. And another important thing that CHIME Pulsar is able to do is that we are able to provide more robust measurements of any variation in dispersion measure of pulsars, as we had higher cadence to sample like small short timescale variation in the dispersion measure, as well as being operating at a much lower observing frequency and larger bandwidth allows us to better model the dispersion measure as the effects of dispersion measure, it's more pronounced at the CHIME band compared to the higher frequency used by Green Bank telescope and Arecibo. So one of the results that we are able to do using our near daily observation of a millisecond pulsar was a timing of this high mass pulsar, J0740 plus 6620, by combining the CHIME pulsar data that we collect with the nanograph data taken with Green Bank telescope, which gives us 30% improvement in measurement of mass and geometric parameter using by trying to measure the effects of Shapiro delay of the signals coming from the pulsar due to its binary companion passing in front of the pulsar. So for this, we are able to get a distance that is consistent with optical association of the white dwarf companion of this pulsar. And the mass measurement is being used by the NICER X-ray experiment to constrain the radius of the pulsar for through measurement of the thermal properties of the pulsar. And here's just a plot showing that the CHIME pulsar's data strength in terms of measuring the DM of the measuring the dispersion measure of the source over time, as even if the residuals of measuring the pulse arrival time is consistent, is a bit worse than what is provided by the Green Bank telescope, we still able to measure the dispersion measure at a much higher accurate precision than what the data from Green Bank telescope is able to do. So another work that we results that we had from the CHIME pulsar data is we are able to measure the Faraday rotation measure of 55 new pulsars, and also provide an improved measurement for another 25 pulsars. And this gave us a better idea of the line of sight magnetic field strength towards different parts of the galaxy in an effort to try to model the magnetic field, the galactic magnetic field environment of our galaxy. So another thing that the CHIME pulsar system is doing is that we use the CHIME pulsar system to follow up on new pulsars and that are detected by the CHIME FRB system, which Ziggy had talked about it a little bit. So far we had seen 31 single pulses of galactic origin that was detected by the CHIME FRB system. So when I say galactic origin, it's made we determine it by the dispersion measure from these single pulses that were detected by CHIME FRB suggest that they are sources that are within our own galaxy rather than extra galactic sources like like the FRBs are. So we use the CHIME pulsar system to undergo follow-up observations to establish the rotational properties of the pulsars, which gives us an idea like what kind of pulsars that they are. So the first 7 discoveries presented in this has been published, and we'll publish and we'll have a second paper that talks about how we determine single pulsars of galactic origin from the CHIME system, and also a bunch of new sources. We are also currently observing about 100 plus pulsars and arets that were discovered by other surveys, which includes the Green Bank Northern Celestial Cap survey done with the Green Bank telescope, as well as P alpha and AO327 surveys. They are done by the Arecibo telescope. And in the future, we'll also start following up on the pulsars to be discovered by the CHIME Slow Pulsar Search project that was mentioned earlier in Ziggy's talk. So another thing that we could do with the CHIME pulsar data is that we are able to look into a phenomenon from pulsars called mode changing and nulling. So what mode changing is that usually the pulses coming from a pulsar has like a very stable imprint, but in some cases, some pulsars would have a change in this like pulse shaped sudden change in the pulse shape, and then which you can see on the right plot, where basically the pulse shape changes suddenly between across a very short time. And nulling is just over a sudden period of time, the pulsation from the pulsar just switch off all of a sudden for, it could be tens of minutes, from few rotations up to tens of minutes, and sometimes even days and months before it switches back on. So one thing that CHIME pulsar is able to do is that this phenomenon happens in quite infrequently, depending on like the pulsars themselves. And the high cadence monitoring of pulsars will be able to help us to uncover this phenomena. So we are able to detect at least 14 new mode changing and nulling pulsars through the data that we have collected over the first year or so of the operation of the telescope. And there are also a lot of other science projects that are currently in progress. So we are looking into mass measurements of other binary pulsars using the same technique that we use for the mass measurement of the pulsars that are presented earlier. We are also doing an aret sensors. So arets are like pulsars. They are pulsar-like object, but the pulsations coming from them are like very, very infrequent. So like they might be only like the signals coming from those pulsars might only appear once every like few tens up to few hundreds rotation. So what we do is that we had 5,000 combined observations of 30 of these known sources taken over 2 years. And from that, we are hopefully able to quantify the population of arets and kind of like give us an idea how many of these sort of very erratic radio emitter exist in our galaxy. And then among the pulsars that were discovered by the CHIME FRB system, there are also a few of them that have very interesting properties. So which will be coming up as a separate publication in the future. And we are also looking into studying the interstellar medium through modeling the scintillation and scattering properties of pulsars. And we are also looking into measuring the DM variation of pulsars over time and use it to model the solar wind, which will contribute to a variation in DM depending on the time and the time of the year where we make the measurements. And the last thing that's here is we are also looking into starting a millisecond pulsar search, which will be sort of like a companion search to the CHIME Slow Pulsar Search project, where we'll be collecting data at the much higher time resolution than what CHIME FRB is able to, so that the data that we collected is more sensitive towards searching for very fast rotating pulsars in with a period of like a few milliseconds. So so far we had collected 3 and more years of data of 400 to 500 pulsar observations per day. So there's a lot more things that we could do with the data that we had collected than what I just mentioned. And there's definitely too much data than what the current CHIME Pulsar team could manage. So if you're interested in any sort of pulsar science, you can get in touch with members of CHIME Pulsars, which are located in these institute, UBC, University of Toronto, McGill, West Virginia University, and the National Radio Astronomy Observatory in US. So, and here's like a points of contact of a couple of the postdocs that are working on the CHIME Pulsar experiment. And I think that's about it that I had to talk about. Thanks for listening.
Great, thank you so very much for that. So I want to open up the floor to anybody who has questions. I have some myself, but I'll give everybody else a chance before I monopolize. So if you just want to raise your hand, or you can just go ahead and open up your mic if you have any questions. Okay, well then I'm going to ask my first one while we're waiting. This is for either one of you. I don't know which would be better posed for this question, but I'm curious, how do you handle and how do you decide what data gets thrown away? Since you have so much, if I remember, it was something like 142 gigabytes a second. How do you deal with that?
So yeah, we let the computer decide, and so most of the sky is there's no signal, and so we just search. And so the way to go about this is I mentioned these time delays that are quantified by the dispersion measure, and so you don't know if you look at any given line of sight what DM you would find FRB at. So you just do trials at all different DMs, and so you effectively integrate over all of these possible sweeps, possible dispersion sweeps, and then you do a peak finding algorithm. And if there's a peak, you save it, and if there's no peak, you throw it away. Okay, I imagine that's also highly optimized. Do you know if there's any machine learning uses for peak finding or other search algorithms? And not for peak finding. Peak finding is like a match filtering algorithm, and it's highly optimized indeed. There's a lot of computers churning away at those data 24/7. When you find a peak, there's, well, let me phrase it another way. There's also radio frequency interference, which is just all types of radio emission from Earth that can produce peaks too. And so the next stage would be we find a peak, but then still the majority of those peaks come from some interference, and some of that is TV station bouncing off airplanes coming back into the telescope, and some of it is maybe just the telephone network, like the 5G towers. And so where the machine learning comes in is then next stage, comparing, is this coming from RFI or is this coming from something astrophysical? Okay, great. Thank you for that. Michael, I see that you have your hand up.
Hi, that was great. Thanks. I wondered about, you said you talked about the single galactic pulses, and then you said you reobserved them to get their rotational characteristics. And my question was, how do you get the rotational characteristics of a single pulse? I'm guessing that these are sort of rat-like things, that they do repeat, just not very often. Is that how it works, or are they really single pulses?
Yeah, so we do follow up more than 31 sources, and some of them are like you see a single pulse, but we never see them again. So for those, you can't even say if it's a source the real source. But when we confirm that a source is real from CHIME FRB detection is real, it means that the pulses does repeat. So from that, you can start like basically measure when you see a pulse from that RAT, and then you can kind of like try to find like what would be a spin period that would explain like the gaps between different sets of single pulse that you see. So yeah,
Okay.
in essentially,
no,
they are repeating sources.
I was just sort of not going, wait, single pulse rotation. Thanks.
The unique feature here of CHIME FRB is it's a passive monitor of the sky. And so because we do the search for fast radio bursts, we for free also search for similar single pulses from in the galaxy, and then we just pass those coordinates on to the Pulsar team.
Yeah. No, that's like, it's cool that you guys are seeing those.
Great. Thank you for that, Michael. And Thomas, I see you'd like to ask a question, so go right ahead.
Thank you both. That was really an interesting presentation. I had two questions actually, but I'll just start with one regarding nanograv. I was curious, what sort of timing resolution do you need to detect these gravitational waves? And also, what are some factors that you think might really enhance the likelihood of obtaining a detection? Like, is it more telescopes, more millisecond pulsars in the data set? I'm just curious what your thoughts were on that.
I'm just gonna say first, I'm not like directly involved in nanograv, but my understanding is that so it's like a lot of different things that could help with improving detection threshold. So one of it is like having as long of the observation time span as possible. So like the whole of nanograv, as far as I know, they are working at trying to new data release, which is 15 years of data that they have collected so far. So like the longer the time span, the smaller the RMS noise that you see in the data. So like basically you could probe deeper into deeper into like how weak the signals are that we could detect, and other things are like I mentioned with the CHIME telescope is that we could reduce that RMS noise much faster than any other telescope just by able to observe the pulsars at a higher cadence. And also another thing that I know of like CHIME is that basically the other thing is that if you can try to model out any sort of like sort of like effects that could affect like various effects that could affect like the pulse, the arrival time of pulses, that would be best. So one thing that a few of the like pulsar timing array experiment does is that they would have telescopes that operates at much lower frequency in trying to like basically model the dispersion measure, because like at high frequency you just couldn't measure them as well as low frequency observation, and from that you could like interpolate the like how the DM is supposed to change in the for a pulsar, and then apply it to data that you collected at higher frequency. And yeah, and that's one of the other thing that you want to remove, like remove as much physical anything, as much things that you could physically explain as possible.
Great, thank you very much.
All right, well, thank you all very much for the questions. Thank you again very much, Ziggy and Chia for coming and giving this presentation. Like I mentioned, that we'll be putting up on our YouTube channel soon. And with that, I will be concluding this session of CaTS. Thank you all once again for coming, and we will see you again soon.